Like a very good afternoon to everyone, to all, uh, to IIT Jodhpur, Dr. Bhupendra Singh, the students of IIT Jodhpur, and all the participants in this session. So, my name is Solomon Debbarma. I'm working as an adjunct lecturer and as a postdoc associate in the Texas State University, United States. So, in this lecture, I'll be talking about the pavement quality mix design as per IRC 44. So so in this session, we are going to learn about, first of all, we'll try to understand what the pavement quality concrete is, its definition, and we'll also try to understand the fundamentals associated with the pavement quality concrete, and we will try to understand the factors affecting the mix design, and then we will try to learn the design procedure as per IRC 44, and then we'll solve the mix design, and in between we'll try to understand the effect of chemical and mineral mixtures on the mix design. So before we move ahead, what actually is pavement quality concrete, or what is known as the PQC? So by definition, PQC is the cement concrete made with large size aggregates, uh, yeah, in accordance with our specifications and laid over a drying concrete subbase. So drying concrete acts as a base layer for the rigid materials, the pavements. So the PQC, which is the pavement quality, is usually used for the highway concrete pavements and the airports because of its ability to sustain high impact loading. So this is the typical cross section of a rigid the pavement. So so the rigid pavements, it consists of different layers. We have the subgrade, and we also have the GSPS. We may have the GSBS separation layer. We may have the drainage layer, and then yes, we also have the drying, the concrete, and then we have the pavement quality concrete slab. So the pavement quality concrete is usually designed for 28 days compressive strength of 40 MPa and the 28 days flexure strength of 4.5 MPa. So IRC 44 recommends that the minimum compressive strength for the PQC slab should be 40 MPa, and the 28 days FR is the flexural strength, should be 4.5 MPa at least. So in this lecture, we are going to talk about how to design the mix for the PQC slab, right? So this is our Indian guidelines, the IRC guidelines for the cement concrete mix design, right? So I think this is the latest revision. So in this revision, there are some modifications made. That was made. So firstly, the target mean strength has been fixed here, and then there is the recommended combined grading requirement for both the coarse and the fine has been also like introduced, and then the maximum size of coarse aggregate has also been modified to 31.5 mm. And then yes, of course, the requirements for selection of standard deviation, air content, water content has been reviewed and modified. And lastly, the adjustments on water and aggregate content has also been modified in this third revision. So but before we go for the mix design, there are some data that we require for the mix design. Some of them are the grade designation. So before we design, we want to know what grade of the concrete do we require. Should we go for an M40 grade, the concrete? Should we go for a higher grade? So these things should be known before the designing of the concrete mix. And then we also need to know the type of the cement. Are we going for the ordinary Portland cement? Are we going for the Portland, the PPC cement? Or are we going for the 43 grade cement, or the 33 grade cement, or the 53 grade cement? So these things should also be known. And yes, the maximum nominal size of aggregate is also very, very, very important. So the effect of this maximum nominal size aggregate in the mix design, we will be discussing in the later slides. And yes, the minimum cement or the cementitious materials content, the maximum water cement ratio, the maximum cement content. So these things should also be known. And yes, the workability is also like important. We do not want to have a stiff mix, or we do not want to have a too high slump mix. And also the degree of the side control, the type of coarse aggregate, fine aggregates, and the chemical admixtures. So sometimes, usually, the concrete pavements are the mix tends to be a little bit stiff. So to improve the workability, sometimes you may need to use the chemical admixtures. And nowadays, there is a huge concern about bringing sustainability. So in such a case, sometimes we may need to use mineral admixtures, right? And then whether the fibers are required, whether the mix design, whether the specified the project would require fibers, manufactured fibers or recycled fibers, is it a steel fibers, right? So this data is required. So this data should be known before designing the mix, right? So before we go for the mix design, there are some mix design fundamentals that we need to understand. So the first thing is like the target strength. So the target strength. So for the concrete mix design, for the PQC mix design, the mix should be designed for a higher target strength in order that 5% of test results should not fall below the characteristic strength. So IRC 44 has recommended two mathematical expressions. F there's CR is equal to FCR plus 1.65 times the S. S is the standard deviation here. So whichever is higher, so we have to choose that as the target mean strength. So now the question comes, why do I need to have a higher strength than I need? So in that case, there is two terms here. One is the target mean strength, other is the characteristic strength. So what are these terms actually? So to understand this, by definition, characteristic strength is that value of strength of concrete at which not more than 5% of test results fall below a specific value. So this 5% is considered from a statistical point of view. So when you consider like in statistical analysis, the repeatability of any test depends upon 95 confidence or 95 significance level. So which means that like 95% of the tests will fall above the specified limit, whereas 5% are expected to fail. So for example, let us say if I will cast 100 cubes of M40 grade the concrete, then out of 100 cubes, 95 cubes will give strength more than 4 Newton per mm square, which means that 5 cubes will not achieve 40 Newton per mm square. So this is known as the characteristic strength. In ACI, characteristic strength is known as the specified strength, right? So, and the target mean strength is the target strength set by the following codal provisions in designing the mix. So, like in structural engineering, we usually come across a term known as the factor of safety. So the target mean strength is more or like the factor of safety. So we need to design the pavement, the PQC mix for a higher strength for the laboratory, for the what do you say, the lab conditions, right? So ISC 44 has recommended these two equations. So the target mean strength can be determined by this equation. So either of these, whichever is higher, we need to choose that value as a target mean strength. So now another thing is that how do we calculate the standard deviation? So the standard deviation can be, IRC has recommended these two equations. So we can use these two equations to calculate the standard deviation. So you see here, this is the standard deviation for a single group, which means that if the mix is coming from a single batching plane or from the ready mix plane for this having the same with no variation, so we can use this equation to calculate the standard deviation. But if the mix is coming from two different planes, batching planes, so we can use these equations to determine the standard deviation. So for determining the standard deviation, we require at least minimum 30 samples, considering from a statistical point of view. But sometimes it becomes too difficult to obtain 30 sample sizes. So in that case, you can use these tables given in IRC 44. So IRC 44 has recommended, based upon the grade of the concrete, either the flexure strength or the compressive strength. Suppose, for example, if the grade of strength is flexure strength is 3.5 to 4.0, so we can use standard deviation as 0.35. Similarly, in case of the compressive strength, IRC has recommended that for M30 to M60, the standard deviation should be assumed as 5.0 Newton per mm square. So these values were obtained based on a comprehensive laboratory investigation by the Indian standards. Right. So yeah, so some other fundamentals are regarding, like, usually as per our Indian standards, we either go for a 150 to 150 to 150 mm for aggregates with NMS. NMS nothing but the nominal maximum size of aggregate greater than 20 mm. And if it is 100 by 100 by 100, we need to go for a nominal maximum size lesser than 20 mm. So what is this nominal maximum size aggregate? So what is the difference between maximum size and the nominal maximum size aggregate? So maximum size aggregate is that largest safe size in which 100% of the materials will pass, whereas the nominal maximum size aggregate is that size in which at least 10% of the material will retain. So let's say, for example, I have a sieve of 31.5 mm, and I have 26.5. So and then I have 19 mm sieve. So in 31.5 mm, so 100% of the material passes. But in 26.5 mm, let's say about 95% of the materials will pass, which means 5% of the material has retained in that sieve sizes. So that is the nominal maximum size of the aggregate. So the nominal maximum size of aggregate, it plays a very important role for the mix design. So how does it place? This can be explained by the wall effect. So which means that when the size of the aggregate is large relative to the mold, the compaction of concrete and the uniformity of the distribution of aggregate particles are affected by the wall of the mold, known as the wall effect. So what happens is that when an isolated coarse particle is in the matrix of fine aggregate, it disturbs the packing density of the fine aggregate. So what happens is, like, the voids increase near the region of the direct contact between the particles. So if the voids is increased, we need more cement, we need more paste, or we can say mortar. Mortar is nothing but sand and the cement, right? So if there is an increase in voids, we will need more mortar to fill the void spaces. So this is known as the wall effect. For example, if I have a nominal maximum size of aggregate as 19 mm and I have decided to use 100 mm mold, so we will require 10% of extra mortar for achieving the proper compaction. So this is why the nominal maximum size of aggregate is very important for the mix design. So some other fundamentals are that we can also go for the 150 into 300 mm cylindrical specimens. And if we go for that, we need to have, and yes, smaller specimens may also be used, but in such a case, the dia by NMSA should be greater than 3. So this is again the wall effect. And yes, the height by dia ratio should be greater than 1. So this is usually important for like the quality control. Like, for example, I want to obtain the core specimens from an already laid structure. So like, I want to obtain a core, so I have obtained a core. So let's say my pavement thickness is maybe about 200 mm, 300 mm, or 400 millimeter. So in such a case, if I obtain the core specimens, I should ensure that the ratios between the height and the dia should be greater than 1, right? And sometimes, like, if we are not able to go for the cubical molds, so, and if there is a provision that only the cylindrical compressive strength can be determined, then we can calculate their cubical strength based on this equation. So cylindrical strength is 0.8 times that of the cube strength, right? And yes, the flexure strength also very important. So the flexure strength, so this is again the wall effect. And yeah, so usually in the past, the concrete pavements has been usually designed based on the compressive strength, but we should understand or we should know that concrete pavements should be rather designed based on the flexure strength, because because concrete pavements fail purely on bending, right? So to determine the flexure strength, we can either go for the third point loading or for the center point loading, but it is recommended to go for the third point loading, because in center point loading, the failure mode will be the combination of both the shear forces and the bending moment. But in the third point loading, the failure mode is purely bending, and since concrete pavements easily fail in bending, so it is recommended to go for the third point loading. But in cases the third point loading test is not available, then we can assume, or we can determine the third point loading strength based on the center point loading, which is center point into 0.85. Right. So yeah, so some other mix design fundamentals. So the first factor that affect the mix design is the water to cementitious materials ratio. So please note that it is you can call it as water by cement ratio or water by cementitious materials ratio. So when I mention one cementitious material ratio, it means that the it can be cement plus fly ash or silica fume or some other mineral admixtures, right? So there is a relation between the water cement ratio to the compressive strength. So you can see from this graph. So this graph said if you increase the water cement ratio, the compressive strength will decrease, and if you reduce the water cement ratio, the compressive strength will increase. So this is usually known as Abraham's law. So Abraham's law is nothing but it is a concept in civil engineering. So this law states that the strength of a concrete mix is inversely related to the mass ratio of water to cement. So we need to have a concrete. So the water cement ratio is very important. And then yes, the degree of the compaction is also plays a very important role in the mix design. So here you can see the hand compaction, it gives us a lower strength, but if you go for the vibration, it will give us a much higher strength, right? And also some of the aggregate the properties, it also plays an important role in the mix design. So apart from the physical like specific gravity, absorption, or and such, the shape of the aggregates also affects the mix design. If you have a spherical shape aggregates, it will give a good workability, but poor aggregate to aggregate interlocking. But if you have an angular aggregate, it gives good interlocking. And yes, the particle size distribution also affects the mix design. So we usually want to go for a well-graded aggregates which have different sizes of aggregates, different sizes of the aggregates. So we need to have the large size aggregates, we need to have the intermediate size aggregates as well, and we need to have the smaller size aggregate as well. So for example, if you go for the poly graded or the gap graded aggregates, so in that case, the voids will increase. And if the voids increases, so the requirement of cement also increases. So that's why the particle size distribution also affects the mix design. And yes, of course, the size, the normal maximum size of aggregate plays an important role, like I have mentioned. So in most of the books or in some of the literature, so what we will find is that if the nominal maximum size like increases, so the strength also will be higher. Why? Because if the aggregate size is larger, the voids will be less, and if the voids are less, which means less less paste. But in case of the high strength, like the concrete, smaller aggregate size may also give high strength because of less severe concentration of stress around the particles, which is caused by differences between the elastic modulus of the paste and the aggregate. But we should also know that smaller aggregate sizes will lead to high paste content, and if the paste is high, it may lead to high bleeding and high shrinkage cracks, and that may affect the strength and durability of the concrete. So this is why we do not want to have a too large size aggregate or too small size aggregate. So that is why we need to have a nominal maximum size. So as per ISC 44, ISC 44 recommends that the maximum nominal size of aggregates should be not more than 31.5 mm. And yes, we also need to understand, we also need to know the optimum doses of coarse and fine aggregates that we need to add in our the concrete mix. For example, let's say if I increase the fine aggregates, the content from 0% to 40% or 50%, the voids will decrease, and if the voids decreases means lesser cement paste content, which means the lesser water cement ratio. And then, but from research, it has been found that beyond certain level, beyond 50%, if you increase the fine aggregates, the content, the voids will rather increase, right? So this is why we need to have an optimum doses of coarse and fine aggregates, which will yield denser matrix. And yes, of course, nowadays, like I have mentioned, sustainability is a growing concept in the highway sectors. So we can also use, like if we would like to go for mineral admixtures like fly ash, silica fume, metakaolin. So the use of these materials can uh, lower the greenhouse gases emissions associated with the manufacturing of cement. So we know that the manufacturing of cement, it contributes to about 8 to 10% of the greenhouse gases emissions. So this is very high. So if we use some mineral admixtures like fly ash, silica fume, we can also bring in environmental benefit. And also at the same time, this will lower the cement content, and this will lower the cost. And also at the same time, due to its silica fume fly ash, this have high reactive silica content, and this can improve the strength and durability. So these are the factors which affects the mix design of the PQC mix. So yeah, so another thing is like the batching approach. So usually for the PQC mix, we have two, or for any like the concrete mix, we have two types of batching approach. One is the volume batching, and the another is the weight batching. Both are equally important, but there is a difference between the volume and the weight batching. So let's say in the case of the volume batching approach, it is important if you want to study the relationships, right? But in the case of the weight batching, so weight method is important for batching, right? Right. And another important thing that we need to understand is the cost. We do not simply want to build or to produce a concrete, or we do not want to simply make a mix which is highly strong and highly durable, but at the same time it is of very high cost. So we want to have an optimized mixture which will be strong, durable, and as well as the cost effective, because cement is very expensive, and the fine aggregates is also expensive, and followed by the coarse aggregates. So we need to make sure that we understand the volume batching process, the weight batching, and we also need to maintain the cost of the mixture, right? So so there are some background data that we need to understand. So we need to know about the specific gravity of the aggregates. For example, specific gravity is very, very like important. So any change in the value or any variation in the specific gravity, because aggregates vary from sources to sources. So any change in this value will either increase or decrease the amount of coarse or the fine aggregates that we need to add to the PQC mix, right? And of course, the particle size distribution is important, as I have mentioned earlier. So if it is well-graded aggregates, will have less voids, which means less cement content, less paste content. But if it is poorly graded or the gap graded, the voids content will be higher, which means then we will need more cement or more paste content to fill up the voids, right? And also we need to understand, we need to have some data about the absorption. So we know that aggregates may contain some moisture, right? And aggregates also contain some voids within them on the surface. So let's say if the aggregates has some has some moisture or has some like absorption. So if we consider a constant water to cement ratio, so some amount of water will be absorbed by the aggregates, which means that the water cement ratio will be affected, and it will affect the degree of the mix, the compaction, right? And also we need to understand the free moisture, the content, because like for example, let's say that aggregates has been subjected to moisture. So if there is moisture, there will be an increase with the water cement ratio. And we have already studied earlier that there is a relationship between the strength and the water cement ratio. Higher the strength, higher the water cement ratio, lower the strength, and lower the water cement ratio, higher will be the strength. So we need to make sure that these parameters are well understood. And also we need to know some other job mix details like the maximum water cement ratio, the nominal size aggregate, the slump requirement, or if any do we need any strength at early days, and so on, etc. Right. So yeah, so according to IRC, there are 9 steps to design the concrete mix, the PQC mix. First is the choice of slump. So first is the choice of slump. So choice of slump is nothing but it is a measure to measure the consistency of fresh the concrete before it sets. So it is just an indirect method to check the workability of freshly made concrete. And Asia has recommended some slump values for various types of the construction. So since we are going for the pavements, the slump is usually about 1 to 3 inch. So which is equal to about 25 plus minus 10 10 mm, right? So you see that the range of workability also differs. Like if you go for like SCC, which is a self compacting concrete, we usually require a high flow, which means we require a high slump. And if you want to go for like RCC roller, the compacted the concrete, or the pervious concrete, we usually would like to go for a low slump mixture. So the choice of slump has been fixed as 25 plus minus 10 mm as per IRC 44. And then the next step is the choice of maximum nominal size aggregate. So as I have mentioned, nominal maximum size aggregate is important, and because of the wall effect. So the nominal maximum size aggregate should be less than 1/5 of the form thickness. So let's say the thickness of the pavement is 200 mm. So my nominal maximum size should be lesser than should be about 40 mm. So IRC 44 recommends that the normal maximum size aggregate should not be greater than 31.5 mm. And then yes, the step 3 is that we need to calculate the water and the air content. And step 4, these are the steps. So we will understand about this steps in the subsequent slides, right? So yeah, so generally we design the PQC mix based upon the 1 meter cube volume condition. So so in this 1 meter cube, we will have the coarse aggregates, we have the fine aggregates, we have the cement, and then we also have water, and then there'll be some amount of air, right? So and sometimes we may have the admixtures, either the chemical admixtures or the mineral admixtures, if applicable, right? So this all should account to about 1 meter cube. So the total volume of the concrete mix can be determined by these values, by this equation. So the total volume is nothing but the summation of the individual volumes of all the ingredients, let's say coarse aggregate, fine aggregate, cement, water, and air. And as we know, the volume of each ingredient is simply the ratio of the mass of material divided by the specific gravity of that material times the unit weight of water, which is taken as 1000 kg per meter cube. So if we use these equations, we can determine the individual volume of each ingredient. And if we have all the volume, we can simply, this should be account to 1 meter cube, right? So the first step is we need to estimate the air, right? So ILC 44 has recommended this table to calculate the air, the content. So the air content, it depends upon the nominal maximum size. So you can see here, as the nominal maximum size increases, so the air content, the entrapped air also reduces. Because why? As the size of the aggregate increases, the surface area also decreases, which means that there is a lesser voids, right? Lesser void. So we can use this table to fix the entrapped air. Let's say our nominal maximum size aggregate is 31.5 mm. So 0.8 we can take as the entrapped air. And then the next step is we have to calculate the water cement or the water cementitious ratio. So like I have mentioned, if the engineer wants to use some mineral admixtures like fly ash, silica fume, so this water cement ratio should be so the amount of fly ash added should also be considered in the cementitious ratio. So it is just not water and then cement, but it should also be water to cement plus fly ash, silica fume, or GGBS, or so on, etc. So yeah, so IFC again has recommended this value. So the water cement ratio can be determined based on the flexural strength. So this is nothing but the water cement ratio law, which is the Abraham's law. So the principle is here is the same. You see here, as the water cement ratio decreases, the strength also increases, right? And if the strength decreases, the water cement ratio also reduces. So depending upon the type of the cement that we require, if we want to go for OPC 43 and if you want to go for OPC 53, we can simply determine the water cement ratio. So let's say since the concrete pavements, the PQC, the minimum 20 days flexural strength is 4.5 MPa. So and if we want to go for OPC 43 grade cement, then we can select our water cement ratio as 0.39, right? And then after that, we can simply calculate the water content and the admixture. Okay, someone has just mentioned that the slides are not. Is it fine? Is my slide visible?
Yeah, Dr. Solomon, you are on the
Someone has
22nd.
mentioned that slides are not changing. Okay, so it's fine. Yeah. So the third step is to select the water. So how do we select the water? So there are some factors which affects the water. For example, firstly, cement. So the quantity of cement also affects the water content. If we have higher cement, we will require higher water because of the increase in the surface area of the cement grains. And if we have, and the size of aggregate also affects the water. If we have large size, which means that the surface area decreases, which means we will need low water. And if we have aggregate shape is round, this will give us less water. And if we have an angular shape, this will give us, we will need more water. And also the texture of the aggregate also affects the water content. If we have a rounded texture, we will need more water, and if we have a smooth texture aggregate, we will need lesser water. And yes, silica fumes like ACMs. ACMs is nothing but supplementary cementitious material. So these are nothing but the mineral admixture. So like, for example, if we use fly ash would require lesser water because of, you can see this is the microscopic image of fly ash. So because of its spherical shape, the fly ash particles, it gives a lubricating effect. So because of that, we require, so there will be lesser requirement of water. But when we consider silica fume has a highest specific surface like area, more than 20,000 kg per meter cube. So in that case, what happens is like the silica fume attaches to the cement grains, and this cement grains acts as a barrier, and this will impede the diffusion process. So which means that if the surface area increases, we will need more water. So yes, the ACMs also has an effect to the water, and we can simply like based on the normal and maximum size, we can select our water the content. Let's say if I have 31.5 normal and maximum size, so I need to select 165 kg per meter cube as the water. But please note that this table is valid for SSD dry condition and slump of 50 mm. So this table is valid only for slump having 50 mm. But since our PQC is the should be designed for 25 plus minus 10 mm, so so we need to increase or decrease the water content by 3% for every 25 mm slump. So we need to decrease by 3%. And then after we have the air content, we have the water cement ratio, we know the water content, we can simply calculate the weight of cement, which is simply divided the weight of water divided by water cement ratio. So it will gives us the weight of cement that we need for the PQC. So the weight that we get, sir, we need to check it for the minimum cement or cementitious content, and we need to check it for the maximum cement the content. So these values has been fixed by RSC. The minimum cement content should not be lesser than should not be lesser than 360 kg per meter cube, and the maximum cement content should be lesser than 450 kg per meter cube, right? So, but in case like if we want to use ACMs like fly ash, GGBS, silica fume, so in such a case, we need to increase the cementitious material content by 10% to account for the ACM reactivity. So let's say if my cement content is 400 kg per meter cube, so you just need to increase the cementitious material content by 10%, which gives us 440 kg per meter cube. So now, if I want to use fly ash at 20%, then my fly ash content should account to 88 kg per meter cube. Then the cement content will become 440 minus 88, which gives us 352 kg per meter cube. So now this OPC content, we need to check again for minimum and maximum OPC content again. So in that case, ISC 44 again has recommended if we use fly ash the minimum OPC content should be greater than 310 kg per meter cube, and if we use GGBFS, the minimum cement content should be greater than or more than 250 kg per meter cube. So we need to remember this. Yeah. So, and the fourth step is, so now we have our air content, we have the water cement ratio, we have the water content, and we know the cement content. So now the only thing remaining is the calculation of the coarse and the fine aggregates, right? So, yeah, so again, we have to calculate the volume of coarse aggregate per unit volume of total aggregates. So so based on the nominal maximum size aggregate, we can, and depending upon the zone of the fine aggregates, we can determine the volume of coarse aggregate. Let's say my nominal maximum size aggregate is 19 mm, and my zone and my grading zone of fine aggregate is, let's say, zone 2. So I need to choose this or select this as my volume of coarse aggregate. So this volume of coarse aggregate does not represent the total volume of coarse aggregates in the 1 meter cube, but this volume of coarse aggregate is corresponds to the let's say the total volume of fine aggregate and coarse aggregate is 1. So this volume is with respect to that of the fine aggregates. And also please remember that we need to remember that this zone 2, zone 3, zone 2, zone 1 does not represent any location or region. These are just the decided based on the grading of the fine aggregates, right? So so accordingly, like I mentioned, based on the nominal size aggregate, we can select our volume of coarse aggregate per with respect to the fine aggregates. But again, this table is valid for water cement ratio of 0.50 only. So in such case, and since our water cement ratio, like from the previous slides, we have determined that the water cement ratio, let's say if it is 0.32, so in such a case, the water cement, the volume of coarse aggregate shall be increased by 0.01 meter cube for every decrease in water cement ratio by 0.05 and vice versa. So if our water cement ratio is 0.32, then the ratio is taken as this and gives us 0.686, right? And then, like I have mentioned earlier, the volume of fine aggregates can be simply determined by 1 subtracted by the volume of coarse aggregate. So this will give us the volume of the fine aggregates in the concrete mixture. And then the next step is the mix design, the calculations. So we can simply, like I have mentioned that we calculate the mix design based on a 1 meter cube volume condition. So now we have to calculate the absolute volume, which is 1 minus the volume of air. And then we can determine the volume of cement. So volume is nothing but the mass upon mass divided by the density of that material, right? So times the unit weight of water. So the volume of cement is, we can use these equations to determine. Now, once we have all the volume of cement, we have the volume of water, we have the volume of super plasticizer if required, and if we have the volume of SCMs or mineral and mixtures if we require. So we can calculate the volume of all aggregate, which is the absolute volume of concrete, subtracted by the summation of volume of coarse cement, water, and super plasticizer or cement. And then we need to determine the mass of coarse aggregate, how much of coarse aggregate, how much of fine aggregates do we need. So from the previous slide, I think we can remember that volume is nothing but the mass upon by density times the unit weight of water, right? So we can use this equation to calculate the mass of coarse and the fine aggregate, which is the volume of total aggregate times the volume of coarse aggregate specific gravity multiplied by 1000. So this will give you the mass of coarse aggregate in kg per meter cube. So let us take an example from IRC 44. So these are some stipulations for the mix design. Let's say a client wants to design a PQC mix for 4.5 Newton per mm square flexure strength, and the type of cement is mentioned as OPC 43 grade, and the maximum nominal size aggregate is 31.5 mm, and we need to have a slump of 25 plus minus 10 mm slump, and the maximum content should not be more than 450. So these are some of the test data for the materials, like the specific gravity of the aggregates, the water absorption, the sieve analysis. So these are the data. So the first step is like we have discussed earlier, we need to select a target mean strength. So we have two equations. First, this is one equation. This is the second equation. So based on this equation and based on the flexure strength, based on the standard deviation. So if I want to design for 4.5 ampere, so I need to assume a standard deviation of 0.4. So this gives us, using equation 1, it gives us 5.16 Newton per mm square, and using equation 2, it gives us 5.05 Newton per mm square. So obviously 5.16 is higher than 5.05, which means that 5.16 is the target mean strength. So we need to achieve this strength in the laboratory. In the field condition, we may not be able to achieve 5.16 Newton per mm square, but the correct resistance 4.5 mm, this should be achieved in the field. But in the laboratory, since we have designed based on the target mean strength, so about 95% of the specimens should at least achieve 5.16 Newton per mm square, right? And yes, based on, and in the second step, we have the nominal maximum size is 31.5 mm. So the corresponding entrapped air content is 0.8%, right? So this is for nominal maximum size aggregate of 31.5 mm. And then since our flexure strength was, since our target strength was 5.6 Newton per mm square, so the water cement ratio can be interpolated. You see, 5.1 to 5.5. So the water cement ratio should lie between 0.34 to 0.28. So we have we got our water cement ratio as 0.32. So this water cement 0.32 is lower than the maximum value of 0.4. So which means the initial water cement ratio that we selected is okay, and so we can move ahead with the next step, which is calculation of water content. So we have a 31.5 mm normal maximum size grade, and the corresponding water content is 165. But you must remember that this table is valid for 50 mm slump. But since our PQC is designed for 25 mm, we need to make some adjustments in the water content. So the water content for 31.5 mm aggregate, based on this table, gives us 165 kg per meter cube for 50 mm slump. So after making the adjustment, so we get a water content of 160 kg per meter cube. So now, because the PQC mix has a very low slump of 25 mm, so sometimes the workability might not be good. So to improve the workability, sometimes it might be decided to use some high range water reducing admixtures like super plasticizer. So if super plasticizer is proposed to use, so let's say 20% of water content has to be reduced. So in that case, our water content comes up to be 160 times 0.8, which comes to be 120 kg per meter cube, right? So, and then since we have the water content, we can calculate the cement content, which is the water content divided by the water cement ratio, which gives us 400 kg per meter cube. So now we have to check this. If it lies between the recommended limits of IRC specification, so 360 is lesser than 400 kg per 400 kg per meter cube is greater than the minimum cement content. So hence it is okay, it is safe to go for this cement content. And yes, the maximum it is also lesser than the maximum cement content, so hence this is okay. So now the next step is the calculation of the volume of coarse and the volume of fine aggregates, right? So we have 31.5 mm normal maximum size, and we have been mentioned that the grading zone is 2. So the volume of coarse aggregates should be 0.65. But again, we must remember that this table is valid for water cement ratio of 0.50 only. So we need to make adjustment again. So after making adjustment, the actual volume of coarse aggregate with respect to the fine aggregate comes to be 0.686. So this is usually done to reduce the sand content. So since we know the volume of the coarse aggregate with respect to fine aggregates, we can simply calculate the volume of fine aggregate content, which is 1 minus 0.686, which gives us 0.314 per unit total volume of aggregates, which means with respect to the coarse aggregate. So the coarse aggregate will have 0.686 and the fine aggregates volume should be 0.314, right? So now, like so we have so with respect to the total volume of aggregates only, not considering the total volume of the concrete. So let us not consider air, water, cement. So for that we have the volume of coarse aggregate and the volume of fine aggregate as 0.32 and 0.68. Now we have to do some volumetric calculations. So, and then after we perform the volumetric the calculations, we need to convert it into mass, because we need to provide the design to the client based on the mass, right? So like I have mentioned earlier, density is simply the mass divided by volume. So the mass can be simply determined, which is volume into specific gravity multiplied by 1000, which is the unit weight of water, right? So these are the equations that we can use for the determination of the volume of uh, the total aggregates, right? So yeah, so if we go for the mix, the calculations, so the absolute volume is 1 subtracted by the volume of air. So we know that we found that the entropy air content is comes to be 0.8 percentage. So our absolute volume should be 0.992 meter cube, and then we can calculate the volume of cement. So our volume of cement comes to be 0.127 meter cube, and then subsequently we can calculate the volume of water, and then we can also calculate the volume of the chemical admixture if required. So it comes to be 0.0033 meter cube, and then finally we can calculate the volume of all in aggregate. So this will be A. A is the absolute volume subtracted by the summation of B plus C plus D, which means the volume of cement, the volume of water, and the volume of chemical admixtures used in the PQC mix. So we get our the volume of all in aggregate as 0.3737 meter cube. Now we can calculate the mass of the coarse aggregate. So in the previous slide, I have mentioned the mass can be calculated using this equation, which is the volume of all in aggregate multiplied by specific gravity of that material times the unit weight of water. So if we use these equations, so we can calculate the mass of coarse aggregate, which is E. E is the volume of all in aggregate times the volume of coarse aggregate, which is 0.686, and the specific gravity of coarse aggregate, which is 2.74, which is given already, and the unit weight of water, so which gives us 1379 kg per meter cube. And then like accordingly we can calculate the mass of the fine aggregate, and it comes to be 604 kg per meter cube. So now we have the mass of coarse aggregate, we have the mass of fine aggregates, and we have the mass of cement and the mass of water as well. So this mixed proportions is based on the SSD the condition. So based on the SSD condition, we have a cement as 400 kg per meter cube, water as 128, fine aggregate as 604 kg per meter cube, and we have used chemical mixtures of 4 kg per meter cube, and we have a water cement ratio as 0.32. So now we can make so this table can be used to provide the mix design to the client. So this is the cement, water, coarse aggregate, fine aggregate, super plasticizer. So these values are nothing but the ratio of its material with cement. So the ratio of water to cement is 0.3, coarse aggregate to cement is 1.5 and so on. But this is only based on the surface saturated dry state. But we need to provide a mixture based on the dry state as dry state, right? So in the last step is we need to make some adjustment of moisture. So there is a term called bulking of sand. So what is this bulking of sand actually? So what happens is that, like, in the presence of the moisture, the volume of dry sand increases. Like, if dry sand comes in contact with moisture, a thin film is formed around the particles, which causes them to get apart from each other, which means that the volume of dry sand will increase due to the absorption of moisture, although the density will be the same. The density will remain the same, but the volume of the sand will increases, right? So this is known as bulking of sand. So we need to make some adjustment for moisture, right? So now question comes, how do you make the moisture adjustment? So yeah, so we can do, so in that case, for that we need to make adjustments and we need to provide the mixed conditions based on the dry state, the dry condition. So let's say we got our cement contains 400 kg per meter cube. So, and then the coarse aggregate, we need to make adjustment for moisture. So how do we make? It is simply the SSD weight subtracted by absorption in percentage times the SSD weight. So if we put the values here, we get the coarse aggregate as 1372 kg per meter cube, which is lesser than that in the SSD state, right? Similarly, for the fine aggregates, we get the value as 598 kg per meter cube. And the water, because it is in a dry state, so the amount of water required will be increased, right? So this is how we can make the adjustment of moisture. So we have to provide the mix design in the dry state. So if you want to go for the dry condition, so you can use this mix design. If the aggregate is in the SSD condition, we can use this mix design. So we need to make adjustment for moisture. Now, like, so now in case if we want to use supplementary cementitious materials or mineral mixes like fly ash, so how do we design the PQC mix? Is it a different mix design or is it a similar approach? So I would say that the mix design is almost the same. We just need to make some adjustments during the calculations of the cementitious material, the content. So we have our water cement is fixed at 0.32, and we have our cement content as 400 kg per meter cube, right? Which is the water content divided by the water cement ratio, which gives us the cement content. Now, since we want to use mineral admixtures, here we are using fly ash. So how to decide on the amount of fly ash? So this can be decided. The percentage of fly ash should be decided based on the project requirement and the quality of the material. So do I need to have, like, how much percentage of fly ash should I use? Should I go for 20 percentage, 10 percentage, 25, 30 percentage? And what is the quality of the fly ash? Is it a fly ash grade 1 or is it a fly ash grade 2? So IRC 44 and IRC 15 recommends that for the PQC mix, we should go for fly ash grade 1. And yes, like I had mentioned earlier, if we intend to if we intend to utilize mineral admixtures, so we need to increase the cementitious material content by 10%. So this 10% is the lowest amount. We can increase it to 15% to account for the fly ash reactivity. So now our total cementitious material contents becomes 400 into 1.1, which gives us 440 kg per meter cube. Now we have, since our water content is 128 kg per meter cube, so the water cement ratio will be changed. So the actual water cement ratio comes to be 128 divided by 440, which gives us 0.29, right? So now let's say I want to use fly ash at 20% of the total cementitious content. So it gives us about 88 kg per meter cube of fly ash. So this is the amount of fly ash that we need to add in the PQC mix, and subsequently the OPC content becomes how much we have total cementitious metal content as 440. So we can subtract the fly ash content from the total cementitious materials content, so which gives us 352 per kg per meter cube. So again, so now we have our OPC content of this much amount. So again, now we have to check for minimum and maximum cement content. So if you remember from the previous slides, I have mentioned that IRC 44 has mentioned that if fly ash is to be utilized, so the maximum OPC content should be greater than should be lesser than 450 kg per meter cube. So since our cement content is lesser, so it is safe to use, and the minimum OPC content should be 300 kg per meter cube. And since our selected cement content is greater than the minimum OPC content as per IRC 44 and IRC 15, so it is safe, it is okay to go for this cement the content. So the remaining steps are more or like the same. We need to determine the volume of the coarse aggregate per unit volume of total aggregate. So we have already learned how to determine the volume of the coarse aggregate. So again, so the so the volume of coarse aggregate with respect to fine aggregates comes to be 0.692, and the volume of fine aggregates we can determine and it comes to be 0.38. And then the remaining steps are more or like the same. So we again have to calculate the absolute volume, the volume of cement, and here we need to also calculate the volume of fly ash. So the specific gravity of fly ash is usually around 2.2, and yes, we can calculate the volume of water, the volume of chemical admixtures, and then the volume of oil in the aggregate, and subsequently we have the mass of coarse aggregate as 1344 kg per meter cube, and fine aggregate as 572 kg per meter cube. So now this is our mix proportions based on the SSD state, SSD the condition. So this is the SSD condition, but again, like I have mentioned earlier, we need to make adjustment for moisture. So if you make adjustment for moisture, this is the mix design based on the dry condition. So finally, we have understood how to design the concrete mix. We have learned the fundamentals of the PQC mix design. We have learned, we have understood the factors affecting. We have learned the steps, the procedures, and then we have also solved an example, and then we have also taken a case study of we have taken an example of how to design if we propose to use fly ash in the PQC mix. So yes, so finally we come to the end of the presentation. So yeah, thank you so much everyone for your patience.